Hello, welcome to our presentation on IC engines. My name is Paul Matesevac, and presenting with me today are Oliver Whitehead and Alexander Naphin, and we are from Section A07, Group 2. So the overall purpose of this experiment series is to characterize system parameters and control for a new engine which can operate on compressed air or a propane fuel source. Specifically, our objectives are to calibrate the force transducer at the beginning of each experimentation session. We want to determine the frictional torque and the flywheel inertia, which will later be used to derive other system parameters. We want to characterize a four-stroke cycle of the engine and create a representative cycle, and then we want to model engine output with a simulated combustion.
The force transducer that's used to determine the torque output of the engine and motor is inherently sensitive and is subject to constantly changing force values. Because of this, it requires frequent calibration, and calibration should be performed at the start of every lab before data is collected. This calibration is done by putting several masses of known weight on a lever arm attached to the motor, which rests on bearings. By measuring the length of the moment arm and recording the voltage output of the force transducer against multiple weights, we can generate a force transducer gain and offset equation that will convert voltage to Newton meters.
So to calibrate the force transducer, what we're doing is taking a number of masses that we know the weight value for, and we're placing those on the force transducer, taking that outputted voltage value, and then calculating the torque that would be on the transducer, and creating a regression from those torque values and their associated voltages. And that's that line of best fit equation that you're seeing on the slide there. So when recording our data, we're running the engine at 0.3, 0.6, and 0.9 volts. And all of those are being done with one or all four flywheels connected to the crankshaft. So those tests are run for 3 seconds, and all of them are starting exactly at top dead center. Before this is done, we're measuring the cylinder dimensions, getting all our measurements in line, and then the computer is outputting all of our data. Using the work energy balance equations, using our inertia flywheel equation, and integration of some of that data that's being output, we're getting or calculating all of our desired variables. So this is an example of that data that's being output as we run those 3-second trials on 0.3, 0.6, and 0.9 volts respectively with the either 1 or 4 flywheels. We have things displayed like encoder angle measured against time, force transducer voltage also measured against time, average velocity, average force voltage, and all of the relevant data that we're going to be using in our analysis and presentation.
Here we see the results of the angular velocity versus angular position for the four flywheel configuration of the engine given a 0.3 volt, 0.6 volt, and 0.9 volt input. We notice that as the voltage input is increased, the angular position at which steady state is reached is moved backwards. Looking at the same relationship, but for the one flywheel configuration, we see that this pattern does hold. We also notice that it accelerates faster into the steady state region comparatively. This makes sense given that there is less inertia to be overcome by the motor. It's also worth noting that there are fairly sizable steady state oscillations present. This could lead to a breakdown of our assumptions, such as the motor friction work equivalency, which we use to determine the frictional torque later on. Here we see the results of the torque versus angular position for the four flywheel configuration with the integration regions of motor work and friction work highlighted. Following this, we have the same relationship but for the one flywheel configuration. It's worth noting once again that the rise to steady state is quicker and less noticeable, and we experience more inconsistencies in the waveform in the steady state region.
The work kinetic energy theorem states that the sum of all external work on the system is equivalent to the change in kinetic energy of the system. Using this, we can determine that the change in energy from initial state A to a final state B is equivalent to the change in kinetic energy of the flywheel and the sum of the work of the motor, piston, air, and friction. To derive our necessary values, we will look at the steady state data, where we know the final and initial rotational velocities of the flywheel will be the same. This means that there's no change in kinetic energy, and therefore it will equal 0. Also, we have the cylinder head removed, therefore the work due to air and the work of the piston are both 0. From this, you can see that the work from the motor in steady state is only working to counter the work due to friction, and the torque of the friction is equivalent to the work of the motor divided by the total change in angle from A to B. Looking at the full data set, we know that the flywheel is initially at rest, and therefore the left side of the equation becomes simply the final kinetic energy of the flywheel. We can use this to calculate the experimental value of the flywheel moment of inertia, using the values of motor work and the torque due to friction as recorded and derived from the previous experiments. Looking at this graph of torque due to friction versus velocity, we can see how the torque has a linear relationship with the steady state velocity. As the input voltage and therefore the steady state velocity increases, the torque due to friction also increases, representing a Newtonian friction model.
So here we have our theoretical inertia of the flywheel calculation. This was done making the assumption that the crankshaft is acting like a solid cylinder. Therefore, we're using the equation inertia equals half mass times radius of the cylinder squared. So when inputting those values that we measured, again, the given value for radius was 0.07 meters, but per our measurements, we got 0.073. When adding that in to the equation for inertia, you get 0.00277 kilograms meters squared. So then when factoring that, or when comparing that to the experimental values that we got using our equation in slide 6, we have again our displayed error, and that's in the table below. The reason why this error is so great or of such a significant degree is because we're again using the assumption that the crankshaft is a solid cylinder, which is incorrect. Not only is it not a solid cylinder, there's an added chuck. There's also bolts that I think 4 that are going around the center of rotation of the cylinder or of the crankshaft. So there's a lot of factors that we're not counting in, and that's a big reason for that error that we're seeing. So in week 2, we're going to be obtaining torque and angular position data, as well as piston location versus angular position data for 3 angular velocities. Those are going to be designated low, medium, and high. As well, we're going to get an average cycle laid out for the collected data. And in addition, by performing integration and analysis using our work energy balance and provided equations, we're going to find uncertainty of our values as well as W, or work of air. In week 3, we're going to be determining critical voltage where the engine runs just before stalling. We're going to be determining angular position and crankshaft angle associated or as it relates to the injection window, the angle range that is going to maximize our work output, and we're going to update our work energy model to account for air injection during power stroke.